Hi everyone, my name is Ryan Booz. I'm a Postgres advocate with Redgate Software, and I am back at the beginning of 2023 solving some more puzzles from Advent of Code 2022 using Postgres and SQL, doing my very best to solve these puzzles without going in and using a language, whether it's Python or PLPG or something like that, trying just to use the features native to Postgres itself as a native install before getting into some kind of procedural language under the covers. And so let's look at day 8 and how I solved day 8. So day 8 was about a treehouse, and the idea was that we had this grid. The elves come upon a grid of trees, and the numbers here are the height of the tree, and we are trying to find the total number of trees that are visible from the outside world. Visible means that if you can see a tree, like if I were thinking about the number 3 in the middle here, if you can see the tree from any direction, up, down, left, or right, then it is visible to the outside world. So obviously all the trees on the outside are visible. And then as you look across and up and down each row, if you can see a tree from the outside in all 4 directions, I think in any direction, then it is visible. And so we're trying to find the total number of visible trees, and that will give them a clump of, the trees that are hidden and the best place to build a tree house. So unfortunately, I actually read this incorrectly the first time around, and I thought that I was just looking at the trees immediately adjacent. So just one tree up, down, left, and right. And so when I did that, I was trying to figure out quickly. And again, I didn't think very quickly about how to take these strings and turn it into a grid I could use. We're going to look at that in a second. So I quickly saw this as just rows of arrays. And if I could, identify I'm looking at the first value of an array, it would be simple to look at the first value of the previous array and the next array, and it's just what I thought I would do. And so I thought I'd quickly show you a couple of the ways that I did that in SQL, even though it was the wrong solution. I've used a couple of these functions in previous puzzles so far, and I haven't spent much time talking about them, so I thought I would just briefly talk about a couple of these functions in Postgres. One is string to array, and so when I need to take some kind of string, there's been a number of times now where we've had values of some sort that I want to get multiple pieces of a string or a number. You can say string to array, give it the string, and then a delimiter. In this case, if the delimiter is null, it says take every character of the string. If let's say this is a string of words with spaces. If I put space in there, then I would get an array of individual words. So an array of strings of the words minus the spaces. So in this case, when I do that, I get 30373, which is this value turned into an array of strings, individual characters. Now, knowing it's an array of strings, I could then do a type of, which is another function in Postgres to get the kind of type. In dbeaver, it's kind of nice, and a lot of other IDs will do this. On the lower right-hand side here, I got to get my cursor over here, you'll see that you can click on the value and it will show you what the values are. And at the top, it actually tells you what type of value it is. So I can tell that those are an array of strings, characters as really text, it's not characters or strings. If I cast it to an integer array, then they become an array of integers. And again, for doing comparisons, it's going to be easier, although the collation, even with a textual set, would probably work just fine. It's just one way to move things around depending on what you need to do with that array. Now, I did that, and let me show you what I wanted to get to, even though I realized this ended up working out. So I took each row of that sample data, turned it into an array of integers so that I could look up and down. So the array before, the array after, one to the right, one to the left. It didn't end up being the right solution, but you see by doing things like string to array, I was able to get it with a fake ID. Again, this is just data itself. I haven't yet put it in the table. And what I was trying to do was get it to look something like this, kind of mentally. Now, again, you'll see that I put a lot of these kind of comments in my SQL. When I'm doing a CTE, remember each one of these areas is a CTE, a common table expression. And so this is like a table that I can then query. And then the next one can reference it. I have lost my, sorry, couldn't see where my little cursor was. It's pretty small. This is the next one. So this one can reference CTEs before it. And so then I can query from it. So I'll put those in my code often, just so I can kind of see step by step what things look like. And then at the very end, I took that matrix, did some stuff that I wanted to do so that I could get it to look like this. And that's essentially what I was trying to get it to. You know, here's the current array that I'm looking at. If I then step number by number, it doesn't matter how I would do that because it wasn't the right answer. But if I stepped number by number 3, 0, 3, 7, I could say that is array value 1, array value 2, array value 3, and I could look at the arrays on either side of me in the proper way. Now, that worked for what I was trying to solve. The end result is I didn't get the right answer with the sample data, and I realized something's up. What was happening is I was solving the wrong problem. I needed to go all the way up the column, all the way down the column, all the way left and all the way right. And so instead, an easier solution is string to table. So this is similar to string to array, but what this does is takes each of those values and turns it into a row, and it becomes a table. All right, now I haven't aliased it, so the column header is still string to table, but I now have each row, and I can say for that row, this was the order of the things I broke apart. And same deal, a null delimiter or separator will just do every character. Now, anytime I have, and I'm going to get rid of this for a second to show you, because this is a common mistake when you're using it. Any of these functions that return a set return, they're called set returning functions. So they return a set of data, which is essentially an in-memory table. When it does that, Postgres has this cool feature called with ordinality. It's like giving this set that was just generated a row number without using a row number window function. It actually is faster because a row number function has to iterate a second time over the data set to give it the row number. So as long as you don't need a group by multiple things, if you just need a row of the order that the items came out of this set returning function, you can use with ordinality. I forget sometimes when I'm doing this and I say, hey, I want the ordinality, and I say with ordinality, and I'll get an error like this, syntax error near with. And the reality is when you want to use ordinality, you have to select from it as if it's a table. All right, so when I say select star from this thing, which is just kind of aliased as a table, now I get the data. And the ordinality will give me the first, whatever I alias this to, the first thing I put here will be the actual value coming out of that set. And the second alias here, I used O for ordinality, is the order that those things came out of the set returning function. So now, hopefully you can quickly see what's happening. So now that I know I can get for every row of data, I can get the order of every single character. So I know what row it's in. And then because I can get the ordinality, that's essentially the column it's in, I can take every row, split it apart into a table. And so that was the much better solution. I'm going to turn this off, turn this back on for a second, show you something later. All right, so I have my sample data. I turn it into a grid. Now, again, I'm doing this row number here because it's not coming out of a table. Remember that when I insert stuff into a table, I'm creating an ID column that's created automatically. That's just getting me a number that I can refer to as the column number in this text. And what this ends up looking like is that grid, but now it's just a long table, but I have an X and a Y coordinate. So now I can say for every, this first number is in row 1, column 1. I can look all the way to the right of me and all the way to the left. I'll look all the way up and all the way down because I know what row and I know what column I'm in. And so this just becomes a bunch of where clauses, right? And then the other thing I did here is I wanted, originally I did it this way, right? I had this little second CTE that would find, I did this so I could be dynamic. When I had the sample data, I wasn't sure how many total rows and how many total columns it would be. And because all of the trees on the outside are visible, I just wanted to be able to say, hey, when a tree, when its X or Y coordinate is either 1, so it's row 1, column 1, or whatever the maximum amount of columns are or the maximum amount of rows are, whenever it's either of those values, X or Y, I just make it visible, right? So that was an easy way to do it. I just quickly said, hey, select this out. Now, what that means, if I do this as a CTE, right? So if I did it that way, I would then have to say, hey, when the tree is 1, the column is 1, I guess this is row. So when the row is 1, or I would have to do a subselect here. Select, in this case, Y from max H. So that was annoying to me. I didn't want that to be the case. And so what you can do instead is this what we call cross join. I'm going to comment this stuff out. And so by doing a cross lateral join down below, right here, I can say essentially, I can just create that table here, give it an alias, and now I can just refer to, right? So I alias this thing here. Let me get rid of that. There we go. So I aliased it here, and then I can just refer to that anywhere above, right? This is a cross join, so it's creating a set that I can refer to elsewhere. Just a way to clean it up. Long and short, when that is done, I can sum all the things that are visible. So basically I go tree by tree because I'm just iterating rows. Every row is a tree. And I say, hey, for this tree, if I am taller than any tree to my right, I'm visible. If I'm taller than any tree to my left, I'm visible. If I'm taller than any tree north, south, whatever, I'm visible. If none of those are true, then I'm hidden. And I sum those up and I get the answer of, whoops, what did I do here? Oh, I got to get rid of that statement there. There we go. I get the answer 21. So that worked. And when I take real data, I went ahead and created a table like I've done before. I imported the data, and I think it's still in there. Oh, I did want to show you one other quick thing. When I analyzed this, for some reason, it felt somewhat slow. Now, again, it's fast, but that ended up being a couple hundred milliseconds, and that felt slow to me. So I did do an explain analyze on this, and I happen to notice in this case, if I go all the way to the bottom, that JIT is enabled by default. The total runtime took 258 milliseconds, and the JIT time was almost 258 milliseconds, right? It was almost all JIT time. So I was like, well, that's interesting. I wonder what happens if I turn JIT off. So I can simply say set JIT off. I'm going to go and analyze that again. You'll notice that was almost instant. So I thought, well, I wonder if this would be faster. So when I run the next time down, or I actually run the full data, it ends up being 100 rows by 100 columns, I think, or maybe 99 by 99. It took like 16, 18, 20 seconds to do all those wheres, all right? Where up, where down, select max. It's just a lot of iteration. And you can see that in the JIT version. Well, I'll show you in the other one. Every time there's a loop, now there's only a few rows here, but every single character I have to loop and go find up and down and left and right. Just a lot of work. So I'm going to turn JIT back on because I'm actually not going to run it fully for you. Because it turns out there's a better solution. Once I solved the problem, I did get it correct. I have the same exact thing, up, down, left, right. That was all good. It took about maybe 17, I guess I will run it. It took, I think it takes about 18 seconds, maybe 19 seconds. I was like, man, that still seems pretty long. I turned JIT off and it actually took longer. So JIT essentially takes some of these where clauses and turns them into essentially functions under the cover that can be executed as C functions so that they can, it's just faster to move across and around data. On a really small data set, it had to take a lot of time to do that work. On a bigger data set, it was worth taking that time to get a better output later, right? So the optimizations actually help with a bigger real data set. It just so happened the smaller data set, it wasn't effective for it because you're spending more time doing the compilation than there is actually data to do the work. So turning JIT off didn't help, and that was the deal. So there was actually a better solution. I got this from Vic Faring after I had solved it. I wanted to see what others did. And this just shows the power of SQL. And this was using a simple window function, right? So the same tree comparison and the same max, but the max is over a window function. And the window function says, hey, from the north means anything that's in my X, the same, so partition by X and order by all the rows. And that says basically anything above me. So then it says rows unbounded preceding, because I'm doing ascending. So here's my row, order by, I'm looking only in the X coordinate and select all the X coordinate above me. So all rows unbounded preceding. And then I flip it. I do order descending. And I say, hey, now same thing, all preceding. So I could have said, you're always looking backwards on a set of data. And so by doing that window function, not even have to touch JIT, I get the end result. Now, I had the wrong answer above because I was playing with this. It is actually 1818. So window function does this in 200 milliseconds, right? So the window function was a much better way to go about this. And it was good for me to think about and learn that, number one, I first started to be too complicated with those arrays. And then the where clauses worked. I had my table. It could search through that table. It just ended up being a much less efficient way of doing it. Now, tree 2 is, again, I'm not going to spend a lot of time here. I think it will only take a few more seconds to run, but basically the exact same data. But this time we're saying, hey, for every tree, how far do we go before a tree is taller than us? And so now we're trying to see, they call that, I think, the scenic score. So the further, the more space around a hidden tree, the more scenic view it has, and that helps find maybe the best location for the treehouse. And so now just doing, again, this was before I had looked up Vic's solution, still doing where clauses, so where it's less than me and the X goes up and down or greater than me in every direction. And then I can take however many spaces I get. It's basically doing a coalesce of how far we're going. And then you just have to look at the formula in day 8. You're basically saying, hey, from where I am, how many spaces up? From where I am, how many spaces down? From where I am, left and right, total all of that difference up, and then multiply it, each one of those together, and that becomes your scenic score. And what we were supposed to find is a scenic score that had, what was the highest scenic score. Again, this takes about maybe 25 seconds, something to that effect. If I would rewrite this with that, with the window function, it would be a lot faster. But hopefully, as this finishes up, just to say that, again, taking a simple puzzle of taking a string of values, turning it into something we can search. We could do it with an array. I could have spent more time there, realized I was wrong, and I moved on. It was easy to turn it into a table that I could search. That didn't fully work. It worked. It just was slow. And then we could have done the same thing by taking that table and simply using Postgres window functions. And so there we go. We did the scores and we got our data. And that's a good way to finish out puzzle 8. Hopefully you've learned one or two things. And I know there are other ways to solve this in SQL. And so I'm sure you'll hear about some of those and look forward to talking with you later. Thanks so much. Bye.